Okay, so it's kind of time by my watch. So let me just welcome you first of all to session 2 of day 2 of RTA 2022. Again, we are delighted to have Debmalya Panigrahi for the second part of his talk. So those of you who could not join yesterday, Debmalya is an associate professor of computer science at Duke University, and he works on a variety of algorithmic problems. And for this talk, he has been talking about some of the recent breakthroughs he have had with his co-authors on the minimum cut problem in graphs. So yesterday we heard about the isolating cut lemma, and today Debmalya is going to give part 2 of his talk. So over to you, Debmalya.
Thank you, Shamantak. As I mentioned yesterday, please stop me at any time and ask questions. I would appreciate that rather than postponing all the questions to the end. Okay, so yesterday I talked about the isolating cuts lemma. So let me quickly recall what that lemma said. So the isolating cuts problem is the following. I give you a graph and a subset of vertices in that graph. And I asked you to find the minimum cuts that separate each individual vertex in this subset from all the other vertices of the subset. So for every vertex little t in this subset capital T, I want the minimum cut that separates little t from the rest of the vertices capital T minus little t. Okay, so that's what the isolating cuts problem is. It's asking for capital T number of the number of cuts it's asking for is the size of the set capital T. And we saw that this problem can be solved using log t calls to any max flow algorithm, which is maybe a little surprising in that it exponentially improves over the naive algorithm that requires t calls. Okay, so what I'll do today is, let's see if this is working. Okay, so yesterday we saw that this lemma gives rise to a new global min-cut algorithm. Today we'll see a variety of other uses of this lemma to get a set of new results for other cut problems. So the way I've organized the talk today is I'll sort of quickly go over a few different applications of the isolating cuts lemma in the first half of the talk. I'll go a little fast, but as I said, stop me if you want to. And then in the second half of the talk, I'll sort of dig a little deeper into one particular result or one pair of results on something called a Gomori-Hu tree problem. All right, so the first problem I want to talk about is what's known as the Steiner min-cut problem. This is pretty similar to global min-cut with the following difference. So now I give you a graph and I also give you a subset of vertices that we call terminals. Okay, and what I want you to do is to find the smallest cut that has at least one terminal on both sides of the cut. Okay, so it should split the set of terminals. How it splits the terminals, it doesn't matter. So among all the cuts that do split the terminals, I want you to find the smallest. And as you can see, this actually generalizes the two min-cut problems we talked about yesterday, the global min-cut problem and the ST min-cut problem. So if you choose the two vertices S and T to be in the subset, then the ST min-cut problem is the Steiner min-cut, is the same as the Steiner min-cut. If you chose all your vertices to be in this subset S, then of course all you are asking for is that there's at least one vertex on either side of the cut, which is true of all cuts. So then this is simply the global min-cut problem. Okay. So this is a generalization of these two problems. And the interesting thing is that for this problem, even if we allowed randomization, nothing better than the naive algorithm that runs S-1 max flows was known. Okay, so what's the naive algorithm? You fix one of the terminals as a vertex S, and now find ST min-cuts of iterating through all the other terminals as T, and then return the smallest of these min-cuts. So this was an algorithm we talked about extensively yesterday in the context of global min-cuts. You can run exactly the same algorithm for Steiner min cuts, where you restrict your iterations to only the terminals rather than all vertices. But that's pretty much all that was known. Nothing better was known, even if you allowed randomization. Okay. And here's a very simple Steiner min cut algorithm using the isolating cuts lemma. So in particular, the result that we get is that there's a deterministic algorithm for this problem that uses log n max flow calls. Now, I'm not going to give you the deterministic algorithm because it again involves this de-randomization, which is kind of complicated. But here's a simple randomized algorithm. And as I said, there was nothing known even if you allowed randomization. So I do exactly the same as I was doing for global min cut. So I repeat log n times. This repetition, the outer loop, is because I'm searching for the right value of the right number of terminals on the smaller side. And then within that outer loop, I again repeat log n times. This repetition is just to boost the probability of success. And then I sample vertices, but instead of sampling all vertices, now I sample terminals. So I sample terminals at rate 1/2 to the I. The understanding is that if I got the right value of I, then there are 2 to the I terminals on the smaller side of the Steiner min cut. And then with constant probability, I will hit exactly one of those terminals in my sampling. Now, if I did that, if I hit exactly one terminal in my sample, then of course, once I run isolating cuts on this sample, I will get back the Steiner min cut. Okay, so I return the smallest cut found by the isolating cuts lemma across all these iterations, and that's my Steiner min cut. Of course, if the sample doesn't give me any vertex at all, then I don't run isolating cuts at all.
So Debmalya, there is a question. So Venkatesh is asking here, n is the number of terminals or the number of vertices?
Yeah, you can switch, like you can make n the number of terminals. That would also work. I have just used n because the number of vertices is an upper bound on the number of terminals, and for all we know, the number of terminals is let's say a constant fraction of n. Okay, but you can change n to the number of terminals if you want. Okay. And as I said, it's correct because of exactly the same reasons as the global min cut algorithm was correct. I won't go over this. And of course, the running time is dominated by the calls to the isolating cuts lemma. So as we saw yesterday, the isolating cuts lemma can be solved using polylog or just log n calls to max flow. So this gives you overall an algorithm that uses polylog and max flow calls. So this is actually, so I wrote log n in the black box on top. That should actually be polylog n. That's a typo. Okay, there are multiple logs there. Okay, so that gives a new Steiner min cut algorithm. This is pretty much an immediate extension of the global min cut algorithm. But you can do a lot more with isolating cuts. So here's a different problem. So this is called the vertex connectivity problem. So a vertex cut is very similar to an edge cut, except that what you are removing from the graph is not a set of edges, but a set of vertices. So a vertex cut is simply a set of vertices whose removal disconnects the graph. Just like an edge cut is a set of edges whose removal disconnects the graph. And the vertex connectivity of a graph is the smallest vertex cut in the graph. Okay, so it's the smallest collection of vertices whose removal disconnects the graph into two isolated components. So the vertex connectivity problem asks you to find a minimum vertex cut, a vertex cut of minimum cardinality. And as an example, here I have a vertex cut that's of size 2, and this happens to be the minimum vertex cut of this particular graph. We typically denote the size of this minimum vertex cut by the letter k, sometimes by kappa. And one thing to note is that there are 3 subsets of vertices we are always going to be dealing with vertex cuts. There's the set of vertices that's actually in the vertex cut. So this is usually called the separator and denoted S. So this is the brown set that I have circled. And then this splits the graph into 2 parts. It could be more than 2 parts, but at least 2 parts. Let's call one of those parts L for left the other part R for right. Okay, so that's the notation that we use. And this is again just like global min cuts. This is a classic problem in combinatorial optimization, has been studied for many years. The best running time that was known was from about 25 years ago. This is a paper of Hensinger, Rao, and Gabel. And this gives a running time of m times n. Again, m is the number of edges of the graph, n is the number of vertices of the graph. O tilde, as usual, suppresses subpolynomial terms, in particular polylog terms. So that was what was known. We give this new theorem in a work with Jason Lee, Danupan Nanunkai, Thachapal Saranurak, and Sorachai. So we show that there is a deterministic algorithm for the vertex connectivity problem that uses only polylog and max flow calls. Okay, and if you use current max flow bounds, then this gives a running time of about m to the 4/3, and this unconditionally improves on the previous bound of m times n. Okay, so even if m is like n squared, this still is like m times n to the 2/3 versus m times n earlier. So as you can imagine, it's again going to be using isolating cuts. Every time you see polylog and max flow calls, the right guess is there's isolating cuts involved somehow. But now we will be using the isolating vertex cuts problem. So this is exactly like, yeah.
I have just one clarifying question. So when you are using this black box max flow calls, right? Any algorithm is fine, right? Or does it need to have any? Okay.
Any algorithm is fine.
Okay.
In fact, the flow is not even important. So I'm saying max flow, but from the flow, I will just retrieve an ST min cut. Okay, and this retrieval is kind of trivial. You can use, for example, you can use the residual network to do that.
So yeah. So just one question, Debmalya. So using this new max flow algorithm, does it imply that now all these algorithms will run in almost linear time?
Yes. So I'll get to that at the end. But yes, short answer is yes. Okay, so what's the isolating vertex cuts problem? So it's exactly like the isolating cuts problem, except that we are dealing with vertex cuts. So I'm again given a graph, I'm given a subset of vertices, and now I want to find for every vertex little t in this subset, a minimum vertex cut that separates little t from the rest of the vertices in T. Okay, and using basically exactly the same techniques as earlier, we can show that the isolating vertex cuts problem can also be solved in log T max flow calls. Okay, so how does that help us? So let's take two different situations. So if the first situation is one where the separator S is actually a small set. Okay, in particular, it's smaller than both L and R. And of course, L and R are interchangeable. It's just left and right. So let's think of R without loss of generality as the larger of the two sets. So R is always larger than L. S in this first case is smaller than L. Okay, let's call that the balanced case. Now, in this case, what we can hope to do is we can hope to sample a vertex subset. Again, I'm using sampling. You can try de-randomizing, but sample a vertex subset such that the following holds: that you sample at least one vertex from R. That part is easy. R is the largest of the three sets. But you sample exactly one vertex from L, and you sample no vertices from S. Okay, and this is possible because S is smaller than L. So if you are sampling at the correct rate with some reasonable probability, you will get this property. For instance, with constant probability, you'll get this property. So once you have such a sample, then you are back to your favorite techniques. So now just use isolating vertex cuts lemma on this sample, and you are done. Of course, there's the other case, the unbalanced case, where the separator is actually larger than the smaller of the two sides. Okay, so L is smaller than R, but S is actually larger than L. In this case, this technique doesn't work anymore because you can't hope to sample a set that misses S but hit cell. Okay, like this difference between the sizes of S and L can be arbitrarily large. So in general, you can't hope to get such a sample. So isolating cuts is not very useful here. So for this case, we actually need to devise a completely independent technique that we call kernelization. So this is some version of sparsification, but specifically for vertex cuts. I'm not going to be talking about that. That's the sort of new part in this paper. But what I wanted to illustrate is that at least for one of these two cases, even for the vertex connectivity problem, the isolating cuts lemma is crucial. Okay, so that's one problem. There are other problems where this has been used. So one other problem where this has been used is what's known as connectivity augmentation. So in this problem, I'm given some graph, and I want to find a minimum weight set of edges whose addition makes the graph, let's say, tau connected. So when I say that a graph is tau connected, it means that the minimum cut, the value of the global min cut, or the weight of the global min cut becomes tau. Okay, so I want to add a bunch of edges of minimum weight such that the weight of the global min cut of the graph gets raised to tau from whatever it is now. Okay, now of course it's not just raising one cut. Of course there could be cuts that are between the current global min cut and tau. All of those need to be raised to tau in order for the new global min cut to be of value tau. Okay, and this is a well-studied problem. It's also studied because it has connections to something called edge splitting off. That's a primitive that's used frequently in graph algorithms. Now for this, the previous best running time was due to Bengtsson and Karger and used squared time. So they used a version of the recursive contraction algorithm of Karger-Stein to solve this problem. In a result earlier this year, we actually showed that the connectivity augmentation problem can be solved in Polylog and Max Flow calls, again via isolating cuts. It's basically one of the main components of this algorithm is isolating cuts, although there are a few other components that also go into this algorithm. Now, one thing to note here is that unlike in the case of, let's say, Steiner min cuts, there's no reason to believe that a problem like connectivity augmentation actually needs you to run max flows. Okay, so if you might be able to even avoid max flows altogether. Just like in global min cut, this problem also is very related to global min cut. So there's no reason to believe that you need max flows. And in fact, you don't. So in some upcoming work, we show that you can actually solve this problem in near linear time, in O tilde m time. Okay, so this doesn't use isolating cuts. Of course, one restriction or limitation of isolating cuts is that it uses max flows, so it can't go beyond max flow time. Okay, so this uses a very different set of techniques. Not going to be talking about that, but I wanted to mention that this is one problem where you can apply isolating cuts that gives you some new results, but you can do something that's even better. And then isolating cuts has been used by other researchers, for instance, in these two papers by Chekuri and Poandrad and Mukhopadhyay and Nanongkai. And they have extended isolating cuts to things like hypergraphs, symmetric submodular functions, symmetric bisubmodular functions, and so on, with the purpose of using it for things like element connectivity of graphs and hypergraphs. So element connectivity is this sort of hybrid between edge and vertex connectivity, where you partition the vertices into terminals and non-terminals, and the non-terminals operate like edges, the terminals operate like vertices. So it's a bit of a complicated problem, but it has some interesting applications, and you can actually extend isolating cuts to handle these kinds of more general problems. All right, so that brings me to what I'll spend most of today's talk on, and that is about finding multiple minimum cuts. So far we have been focusing on these problems where the goal is to find a single cut. Okay, so whether it was Steiner cut or vertex min cut or global min cut, the goal was to find one minimum cut. But now let's focus on problems where we are required to find multiple cuts. Okay, and in particular, we'll focus on two classic problems. The first is the single source min cuts problem. So you should think back to single source shortest paths, for instance. It's a similar problem for minimum cuts. So here we have a fixed vertex S. This is the source. And our goal is to find ST min cuts for every other vertex T. Okay, so we are actually looking for n-1 cuts rather than just one cut. So that's one problem that we are going to be interested in. Another problem that we are going to be interested in is a richer problem. So here we are not just interested in ST min cuts with a fixed source S, but we are actually interested in ST min cuts for all pairs of vertices S and T. Okay, so we want to find the minimum cuts for all pairs of vertices. Now here's a very simple single source min cuts algorithm. So maybe the first algorithm we would think of. So you have a fixed vertex S. Now I have to find the min cut from S to every other vertex. So what do? I simply iterate over all the other n-1 vertices. And for each such vertex, I find the ST min cut. And I just return all of these ST min cuts. Okay, so clearly, trivially, single source min cuts reduces to using n-1 max flows. Now, interestingly, all pairs min cuts, which does not have this naive reduction, because you're actually, in principle, you're looking for n choose 2 min cuts here. But there's a beautiful result by Gaussian and Hu, one of the classic results in combinatorial optimization. They showed 60 years ago that, in fact, the all pairs min cuts problem also reduces to n-1 max flows. Okay, so I won't be giving you the details of how this algorithm works, but if you're interested, it's a beautiful algorithm. You should go and look up. We will come back and talk a little bit about this result, and we will kind of pick something from this result that's going to be useful for us. But these two results basically establish, or the all pairs min cuts result and the simple observation for single source min cuts establishes that these two problems, single source and all pairs min cuts, can be solved using n-1 max flows. Now, the surprising thing is, more than 60 years after Gaussian and Hu's work, these remained the fastest algorithm for these two problems. So for both the single source min cuts problem and the all pairs min cuts problem, we had no better algorithms. And this certainly was not due to lack of trying. Faster algorithms were known in pretty much every class of graphs you might be interested in. I've just listed a few of them here, but there are other results that I haven't listed. But for instance, if you restricted yourself to unweighted graphs, there are faster algorithms known: simple graphs, planar graphs, surface embeddable graphs, bounded tree width graphs, etc. So for many different classes of graphs, we knew faster algorithms, including some work I did many years back, but nothing was known in the general case. So if I have a general weighted graph, the only algorithm we knew was the old Gaussian and Hu algorithm. And in fact, for single source, it was even more stark in that the only algorithm we knew was this trivial algorithm that iterates over all vertices. Okay. Now, even more surprising, or maybe going one step further, we knew of nothing better even if you allowed approximation. Okay, so even if we said that, okay, so maybe we don't want the exact all pairs min cuts or the exact single source min cuts, but we want some approximate min cut. Even that did not lead to any better algorithms. Okay, of course, the point here being that approximations tend to lead to faster algorithms for many of these problems. For example, for the ST min cut problem, if you allow a 1 plus epsilon approximation, that actually leads to near linear time algorithms that have been known for several years now. Okay, but not for these problems. So the way I want you to think of this is the following structure of problems. So here, as we go down this tree, I'm making the problems more and more specific. So the most general problem is, of course, all pairs min cuts. If I can solve all pairs min cuts, I can answer all the other questions on this slide. Stricter a specialization of all pairs min cuts is the single source min-cuts problem. Okay. Now, as I said, for both of these problems, the two problems on top, the best algorithms we knew were running n-1 max flows. Then a further restriction is the Steiner min-cut problem. Okay, so of course, if you knew a single source min-cut algorithm, you could solve Steiner min-cut by simply selecting one of your terminals as the source. For Steiner min-cuts, we have a better algorithm that we just discussed. We have an algorithm that runs polylog n max flows rather than n-1 max flows. And then, as we discussed, Steiner min-cut is actually a generalization of the global min-cut problem and the ST min-cut problem. And for the global min-cut problem, we already knew a near linear time algorithm. This has been known for many years now. For ST min-cut, we did not know this. So we had an algorithm that runs in m plus n raised to 1.5 time. Okay, so this was the state of the art. And by our isolating cuts lemma, we showed an equivalence between the Steiner min-cut and the ST min-cut problem. So remember, the isolating cuts lemma was used to solve Steiner min-cut by running a bunch of ST min-cuts, polylog ST min-cut calls, or polylog max flow calls. So there's a polylog equivalence between these two problems. Up to polylog factors, they have the same running time. The rest of the picture was exactly as I've drawn it here. Now, one thing you might wonder looking at this is whether there's also an equivalence between the problems on top. So Gomery, the all pairs min-cuts problem and the single source min-cuts problem, both of them have the same running time, n-1 max flows. So you might wonder, can I use any single source min-cuts algorithm to solve all pairs min-cuts, or is the Gomery-Hu algorithm special in some way? So it turns out that these two are in fact also equivalent. So this is new work. So initially this was observed by Abud, Krautgramer, and Tribelsi, and then in a couple of papers we kind of refined this reduction a little bit. So we made the gadget a little weaker than what they had originally devised. But basically, the bottom line in these three results is that you can also establish an equivalence up to polylog factors between the single source and the all pairs min-cuts problem. So really, it reduces to this one big question: can we solve single source min-cuts any faster than the trivial algorithm that runs n-1 max flows? Okay, and this is the question we are going to attack now. Any questions so far? Okay, let's keep going. So before I go further, what I'm going to do is I'm going to talk a little bit. I'm going to take a little bit of a detour, and I'm going to be talking about approximation algorithms. Okay, so remember I said that even if you allow approximations, we didn't know how to go beyond this n-1 max flow algorithm for any of these problems, for either single source or all pairs min-cuts. Okay, so approximation didn't seem to help. Even larger approximation factors, things like constant approximations, log approximations, things like this. Okay, so what I'm going to do is now I'm going to allow a 1 plus epsilon approximation. So that's as mild an approximation as you can imagine. And we are going to explore whether this approximation helps us go beyond these n-1 max flow type algorithms.
So, Debmalya, quick question before you move on. So, for the bottom three, or at least the two leaves at the end, there are algorithms that do not use max flow.
So the global min-cut does not use max flows. It's in fact faster than max flows. ST min-cut is the same as max flows.
Okay, I guess I was wondering whether like the use of max flows for the other one, like the top ones, are sort of crucial. Maybe that's not the point of your like study. Like you do want to sort of reduce it to max flow calls. Or let me ask it in the other direction. Like let's say I give you a black box, like a really fast black box for the Gomery-Hu tree or like the all pairs. Can you use that to find max flows?
So you can find certainly like that. So all pairs min-cuts is a more all pairs min-cuts is a more general problem than just ST min-cut, right?
Yes.
Like from all pairs min cuts, I can retrieve ST min cut.
Right.
I may not be able to retrieve a maximum flow, but in this entire picture, none of these problems is about finding flows. So when I say max flows, it's just because I want to use max flows as a term for ST min cut algorithms.
Okay, just the saturating cut suffices for you.
Yeah. So the usual way that you would find an ST min cut typically would be run a max flow algorithm and then find the saturated cut.
Right, but there are others, like you can use the LP or something like so. That's why the question.
Sure. I mean, if you like want to bypass max flows, everything that I'm saying still holds.
Okay.
Right. Instead of max flows, if you replace that by ST min cuts, everything that I'm saying still holds.
Okay, got it.
Okay. All right. Okay. So as I was saying, so our real focus is on this single source min cuts problem, and we want to do something using approximations. So let's see what changes if you allow approximations. The first thing that changes is that I don't require my max flow algorithms or ST min cut algorithms now become near linear time. Okay, and again, this has been known for several years. So I no longer have this distinction between what I can do in the case of global min cuts and what I can do in the case of ST min cuts. So that's the first thing, first observation. The second observation is that this polylog equivalence between all pairs min cuts and single source min cuts, this equivalence is actually robust to approximation. So if I gave you an approximate single source min cut gadget, then you can actually find an approximate all pairs min cuts solution using polylog calls to this gadget. Okay, so this equivalence is indeed robust to approximation. Unfortunately, the equivalence at the bottom, so remember the equivalence between ST min cuts and Steiner min cuts was via isolating cuts, and isolating cuts is not robust to approximation. So if I, instead of giving you exact max flow calls, if I gave you approximate max flow calls or approximate ST min cut calls, then we don't know how to use those to find an approximate isolating cuts. Okay, so this reduction doesn't quite work in the approximate world, and therefore for Steiner min, even for Steiner min cuts, once you allow approximations, you don't quite get this polylog and max flow running time anymore. Okay, so the point, so when I say you don't get polylog and max flows, what I mean is that you don't get polylog and approximate max flows. Of course, you can ignore approximation and just run polylog and exact max flows. That would still work. But you don't get the added advantage of using approximate max flows, which are faster. Okay, so that's the situation. So as I said, the polylog reduction from all pairs to single source min cuts is robust to approximation. And therefore, the natural question is, can we obtain an efficient algorithm for 1 plus epsilon approximate single source min cuts? If I can do that, then I would solve 1 plus epsilon approximate all pairs min cuts as well. So let's start off with a very simple algorithm. Again, maybe the first algorithm you would think of if I asked you this problem. So let's denote the source vertex S. So remember, it's a single source problem, so you are given a source vertex. Now what I do is I iterate over values of k that are powers of 1 plus epsilon from the minimum to the maximum minimum min cut weight that I can potentially see. Okay, so this, of course, the number of iterations is some polynomial in 1 over epsilon times some log factors in the size of the problem. So I iterate over all these possible values of min cuts. Okay, starting with the smallest possible value going up all the way to the largest value. And these iterations are in levels that are sort of multiplicative levels of 1 plus epsilon. And for each of these geometric levels, what I do is I find all the vertices such that the connectivity, the min cut value from S to that vertex is at most k, is at most the level I am at. Okay, suppose I'm able to do that. So if I'm able to do that, then of course, trivially, I have solved the single source min cuts problem. Because remember, I am going at levels, like each level is 1 plus epsilon times the previous level. So that means that for every vertex, if I identify whether its connectivity is below one of these levels or above it, then I would be able to determine the connectivity of every vertex up to a factor of 1 plus epsilon. Okay. So of course, the catch is, how do I run this last step? How do I find all the vertices such that lambda st is at most k? So that's what we call the cut threshold problem. So what's the cut threshold problem again? I'm given some undirected graph. I'm given a source vertex S. I'm also given a value of the threshold k. And I ask you to find all vertices t such that the connectivity between S and t, so the minimum cut between S and t, is of weight at most k. If I can solve this problem, I'm done with 1 plus epsilon approximate single source min cut.
So what kind of runtime are you shooting for solving the cut threshold problem? Like dependent on k or something?
No, so it will be again like Polylog calls to max flow.
Okay, I see.
So in the blue box, in the single source min cut problem, I have Polylog iterations, or maybe even just log iterations.
I see, because you have discretized the weights. Okay.
Yes. So as long as I can solve cut threshold in Polylog calls to max flow, I'm good.
Yeah.
Okay, so in fact, that's exactly what our theorem is. So we show that there's an algorithm for the cut threshold.
Sorry, just one more clarification. So sure. At all these levels, I mean, why do you need less than k? Don't you just need between k and, let's say, like k times 1 plus epsilon? Because you just need for one level, no?
That's right, but think of this as a sieve, right? So as you go up the levels, at some point vertices drop off from this set.
I see.
Wherever it drops off, that's your correct min cut value up to a factor of 1 plus epsilon.
Okay.
Okay.
Yeah.
So our main theorem, this is a follow-up work with Jason Lee from last year. So we show that there's an algorithm for the cut threshold problem using Polylog and calls to the isolating cuts lemma. And of course, the isolating cuts lemma in turn uses Polylog and calls to max flow. So overall, we are still using Polylog calls to max flow. Now, one thing to note is that these are calls to exact max flow. It's not calls to approximate max flow. Okay, so we are still using exact max flow. As I said, isolating cuts lemma cannot handle approximate max flows. But as a consequence of this, we can now solve the 1 plus epsilon all pairs min cuts problem using Polylog and max flow calls. So we went from max flow to isolating cuts, from isolating cuts to single source, isolating cuts to cut threshold to single source to all pairs. And we keep incurring polylogs in all of these steps. All right, so let's try and dig a little deeper into this cut threshold problem.
So yeah. What's in the previous slide, what's the dependence on epsilon? Like the number of calls?
Yeah, it's just, I think, 1 over epsilon. It's just the number of iterations in this loop.
Okay, so it's not like, not hiding too much.
Yeah, it's just 1 over epsilon. Yeah.
Okay.
So there's no epsilon involved inside the cut threshold problem. Like the cut threshold problem doesn't even have an epsilon. It's only in this outer loop. Okay. All right, so let's see how we can hope to solve the cut threshold problem. So for this, I need to go back to this 60-year-old algorithm of Debmalya and Hu. I won't tell you what the algorithm is, but I'll tell you what they came up with using their algorithm. So they came up with this idea of what's called a Debmalya-Hu tree. So given any undirected graph, this graph may or may not be weighted. The Debmalya-Hu tree of this graph is a weighted tree on the same set of vertices with the following property. If I take any two vertices in this graph, so let's say the vertices S and T that I have shown here. Now, if I look at the tree, I can easily determine the minimum cut between S and T. In particular, it will be it will be the minimum weight edge on the path from S to T because it's a tree. Now take that minimum cut. In this particular case, it's the edge of weight 2 incident on S. Take that edge. Now that defines a bipartition. If you remove that edge from the tree, that defines a bipartition of the vertices into 2 parts. Take that and put that bipartition, sort of project that bipartition back to your original graph, okay, in the way that I have done here. If you do that, the Gomori-Hu tree property says that what you will get in the original graph is also an ST min cut, and the value of that min cut will be exactly equal to the weight of this edge in the tree. Okay, so the ST min cut in the tree corresponds to an ST min cut in the graph, both in terms of how the vertices are bipartitioned and in terms of what the weight of this cut is. So that's what a Gomori-Hu tree is. Now, why do we want to use this, or how do we want to use this? So let's do the following. So let's say that our threshold K in this, let's take a particular example where in this Gomori-Hu, in this graph, we set a threshold of K equals 2. Okay, so we want to find all the vertices whose connectivity from S is no more than 2. Now, one way of identifying these vertices is the following. Let me start walking outward from S on the Gomori-Hu tree. Whenever I encounter an edge of weight 2 or less, I know that all other vertices on the other side of that edge, all those vertices must have connectivity 2 or less from S. Right? So if I walk outward from S, the 2 edges that I encounter that are of weight 2 or less are these 2 edges of weight 1 and 2 in this tree. Then the answer to my cut threshold problem would be exactly the set of vertices that are on the other side of these 2 edges, 2 and 1. Okay, because their connectivity to S would be less than 2 because they have this edge of weight at most 2 on their path to S. Okay, now of course this is completely useless algorithmically because we certainly don't have this tree in at our disposal. If we did, then we would have already solved the all pairs min cuts problem. But just as a thought experiment, these are the set of vertices that I want to identify. Okay. So any questions about this? This is an important point. In the next 2 slides, I'm going to exploit this.
I still have a little bit of difficulty that when you write these weights 2, 1, 4, 4, 3, why can't this one be distributed across this Gomori-Hu tree?
What do you mean by distributed across?
I mean, why is it the minimum weight age is like centered around, like the way you did one here, no? Why can't there be one at some other edge?
There could. Like, it's not necessary that these edges are incident on S. That's not necessary. You're just walking out of S.
Okay.
Wherever you encounter an edge that's 2 or smaller, you say everything, all the entire subtree under that edge are a set of edges, vertices I need to distinguish.
I see. Okay. Okay.
Okay. So it's just coincidence that these edges are incident on S.
Okay. Got it. Thanks.
Okay. So let's set up a little bit of notation. This is the only bit of notation that you're going to see. So let me call a closest vertex to S with this property that lambda, the connectivity is no more than K. Let me call that V. So basically, like pictorially, this is the first vertex you encounter after you cross an edge of value 2 or less. So I've shown this vertex V in this graph. Okay, of course, there's no unique V. There are many candidates for V, but let's take any one such V. Okay. So now let me call the entire subtree that subtended by V, the entire subtree being separated by V from S. Let me call that T sub V. And let me say that the size of this subtree is N sub V. In this particular example, the size of the subtree is 5 vertices. So n sub v would be 5. Okay. Now, remember that this entire subtree must be identified by my algorithm because all of these vertices are going to be in the answer for the cut threshold problem. Now, the key idea is the following. Suppose I sample vertices at rate 1 over n sub v. If I do that, then with constant probability, I'll choose exactly one vertex from this entire subtree T sub v, because T sub v has n sub v vertices. If I sample at rate 1 over n sub v, with constant probability, I'll choose exactly one of these vertices. Now, what is the probability that this specific vertex that I sample is actually the vertex v itself? That probability is about 1 over n sub v. Okay, or constant over n sub v. Okay, so there's constant probability that you choose exactly one vertex. And then given that you have chosen exactly one vertex, what's the chance that you ended up choosing v precisely? That's another 1 over nv. So it's 1 over nv times some constant. So that's the probability with which my sample hits precisely v. Now, if I get such a sample that hits v and nothing else in this subtree T sub v, now what I can do is I can run isolating cuts lemma on this sample. And let's say I dump s into this sample. So I add s to the sample. Now you run isolating cuts lemma. Since v is the only vertex sampled in T sub v, isolating cuts lemma will actually reveal this entire cut T sub v. Okay, because that's the smallest cut that's cutting off v from the rest of the sampled vertices. Okay, so that's the main idea, that we are somehow going to be sampling we are going to be sampling at rate about 1 over n sub v. That will hit v with probability about 1 over n sub v. If it does so, then isolating cuts lemma will give me the answer, will give me entire T sub v's. Okay. Now this should raise two questions.
Could you please repeat the isolating lemma? How do we run the isolating lemma? Could you please repeat the step 4?
Okay. So this is a tool that I discussed yesterday. So this tool does the following. If you give it a subset of vertices, then it finds I
understood the I know the isolating cuts, but I just want to know that how step 4 is being enumerated here.
So if once you sample, you have some sampled set of vertices, right? Add s to that sample, so that gives you a set of vertices. On that set of vertices, you run isolating cuts lemma. Like isolating cuts lemma needs a graph and a subset of vertices to run. So the graph, of course, is the original graph, the input graph. The set of vertices on which you are running isolating cuts is the set of sampled vertices plus s.
Okay.
Does that answer your question?
Yeah, thank you.
Okay. All right, so this should raise sort of two red flags. The first is that we don't know the value of n sub v. Of course, this is something that we have encountered a bunch of times, and as usual, this is not the bigger concern. But really the big concern is, are we revealing vertices fast enough? Right? Remember, the probability that I will choose precisely v in my sample is not very high. It's like 1 over the size of a TV, right? It's 1 over n sub v. N sub v can be large. It can be n over 2, for instance. Then this probability is just 2 over n. So we are revealing all these vertices, but with fairly low probability, with just probability 2 over n, if n sub v is n over 2. So is that good enough? Are we revealing vertices fast enough? Okay. So to answer this, let's first look at the overall algorithm. So what's my overall algorithm? So here's the algorithm. I start off with this set of vertices u, which is everything except s. So u will basically be, I will remove every vertex that I have already identified as an answer to the cut threshold problem from u. So u starts off with everything. Every time I realize that some vertex has connectivity less than k from s, I remove it from you. That will be the way the algorithm proceeds. Okay, now I repeat the whole thing polylog n times. This is just to boost sampling, boost probability of success. So ignore this outer loop, it's not so important. In the inner loop, what we are doing is we are again doing these iterations with I from 0 to log n. So again, what am I trying to do? I'm trying to guess the value of n sub b, right? And my guessed value is 2 to the I, okay, in the iteration where I have set I to a particular value. So now within that iteration, what I do is I sample u, all these vertices that I still don't know whether they are less than k or bigger than k. So I sample u at rate 1 over 2 to the I. Okay, this is what I promised to do on my previous slide. I was trying to sample at rate 1 over n sub v. 2 to the I is my guess for the value of n sub v. So I sample at rate 1 over 2 to the I. I obtain this set t. As I promised, I run isolating cuts on t sub t union s. And once the isolating cuts returns a bunch of cuts to me. If any of these cuts are of value less than or equal to k, I simply remove all the vertices that it reveals to have less connectivity than k from s. I remove all these vertices from u. Okay, and I keep doing this polylog n times. I claim that once I've done this polylog n times, with high probability, I have identified all the vertices that had connectivity less than k. Okay, why is that the case? So what I precisely claim is that in expectation, the size of u drops by a factor of 1 minus 1 over O log n in every step. Okay, so if I started off with, so suppose I had to identify a bunch of vertices, 100 vertices. In every step, in expectation, I will identify 100 divided by log n vertices. Okay, so if I am able to do this in expectation, if the number of vertices that are left to identify, if that number keeps dropping by a factor of 1 minus 1 over log n, then of course after polylog n rounds, I'll be done. All the vertices would have been revealed at that point. All right, so what's the proof sketch? So let's look at any one vertex v. Okay, so what does this vertex v do? So as you see in this figure, vertex v reveals n sub v vertices with probability about 1 over n sub v. Okay, so if I think of the expected number of vertices that v reveals, okay, it's kind of revealing n sub v vertices with probability 1 over n sub v. So it's revealing a constant expected number of vertices. Okay. Now, the point is that if you look at any particular vertex now, it can only get revealed log n times because I'm running this for I equals 0 to log n. So every vertex gets revealed at most log n times. And the total number of vertices I am revealing, the expected number of vertices I am revealing with repetition is the total size of u. So that means that overall, I expect to reveal at least 1 over log n of the total number of vertices I had to reveal. Okay, so if that was a little sort of hand wavy, then that's okay. So we don't need to, you don't need that for the remaining few slides. But if you are interested, I encourage you to take a look at the paper. It's kind of a classic counting argument. Okay. So given this, now what do we have? So we now have a polylog n max flow based algorithm for all of these problems. So remember, this algorithm actually solves single source min cuts. And there's this polylog equivalence between single source and all pairs min cuts, which means now all of these problems, all pairs, single source, and Steiner min cuts, has this algorithm that uses polylog n max flows. The only catch, as I said,
sorry.
Yeah,
I have one doubt. Maybe I missed something. So when you are using isolating cuts for this problem, don't you need that S is actually that singleton on one side of the cut? Specifically S?
No, not S. So V, this, so if my sample had this property, that vertex V is the only vertex in the yellow part of the cut that got sampled.
Yeah.
Then, and all the other vertices, including S, are on the other side. So now when I run isolating cuts,
okay, then you are
V
good.
is one of the candidate vertices in this set. So the isolating cut for V will reveal this yellow cut.
Yeah. Okay. Yeah. Thanks.
Okay. All right. So at this point, we have this algorithm that uses Polylog and exact max flows. Now, of course, there's this catch. It's still using exact max flows, whereas we are finding an approximation, like it's revealing an approximate solution. So can I actually use approximate max flows? Seems difficult because isolating cuts it does not extend to approximate max flows. But we did manage to figure out a workaround. So in some very recent work with Jason Lee, Danupon Nanonkai, and Tachapal Saranurak, we showed that what we can do is we can actually retrieve isolating cuts, not with arbitrary approximate max flows, but with something that we called fair max flows, okay, or fair min cuts. And this fairness property is kind of technical, but this is a restriction on approximate max flows and min cuts. It's some subset of max flows and min cuts that we denote as fair. And we show that this extra restriction of fairness does not affect the running time. So a fair max flow or a fair min cut can also be computed in near linear time. Okay. And the advantage of fair flows and cuts is that they can now be used in the isolating cuts framework. Okay, and using this, we actually reduce the running time of all of these problems, the approximation version of all of these problems, to near linear. Okay, so the last couple of slides is about the exact problem. So let's go back to this exact single source and all pairs problem. So there we are still stuck at n-1 max flows, as we discussed earlier. So how can we improve this? So again, in very recent work, we managed to improve this. In particular, we show that there is an algorithm for the Gomory-Hood tree problem. So it constructs a Gomory-Hood tree, which thereby solving both all pairs min cuts and single source min cuts. So there's an algorithm for this problem that runs in O tilde n squared time. Okay, so remember the previous solutions were all using n max flows. So n max flows is certainly at least n times m. Max flows cannot run faster than m. So this is significantly better than that. And we show this by solving single source min cuts in this time and invoking the reduction between single source and all pairs min cuts. Okay. Now I want to mention that we actually believe that we can actually do this in max flow time. We don't need n squared. But we are still verifying some details in the max flow algorithm. That's a lot more complicated. The n squared algorithm is already on arXiv. Okay, so let me give you a very brief sketch in the 2 or 3 minutes I have left of how this algorithm works. So let's go back to this sort of 1 plus epsilon approximate single source min cut algorithm. So what were we doing? We were setting these sort of geometric levels at powers of 1 plus epsilon, and we were using a sieve. At each level, we were solving cut threshold. So this allows us, using just this, the fact that we can solve cut threshold, this allows us to partition the vertices into these blocks where we have figured out all the vertices whose connectivity is between 2 of these levels. So between, let's say, 1 plus epsilon to the I and 1 plus epsilon to the I plus 1. Now what we do basically is we try to solve this problem where we are given a set of vertices such that their connectivity from this source S is between K and 1 plus epsilon K. Given such a set of vertices, we want to find the precise connectivity values. Okay, if we can do this, then we can plug that into the blue box and we would be done. Okay, so that's our goal. I'm given a bunch of vertices. I know all their connectivities are between k and 1 plus epsilon k. Can I find their connectivity from S? So this algorithm has 3 steps. I'll go briefly over all the 3. So the first step is to find a bunch of edge disjoint Steiner trees, Steiner with T as terminals. Okay, so these are things we call guide trees. And for those of you familiar with packing, so this is a fractional packing algorithm. Okay, what's the key property? So note that the min cuts that we are after are a value between k and 1 plus epsilon k. Now, if we pack a bunch of edge disjoint Steiner trees, then what will happen is that this min cut in expectation in any one of these trees, if I randomly chose one of these trees, then any such min cut can only have 1 plus epsilon edges in such a tree, right? Because the min cut doesn't have more than 1 plus epsilon k edges, and I have k such trees, and these are edge disjoint. So in any one of these trees randomly chosen, I only expect to see about 1 plus epsilon edges from the cut, right? From the cuts that I am after. So that's the key property of these trees. How do we come up with these trees? Well, this requires some work. So we use a bunch of techniques. We first do sparsification. We then use something called the multiplicative weights update method, which many of you might be familiar with. And then the multiplicative weights update requires a gadget. So this gadget problem, we need to use a Steiner tree algorithm. We use a fast algorithm due to Kurt-Malone. Okay, so but the bottom line is that we pack a bunch of trees with the property that if I choose a random tree, I don't expect my min cuts to have too many edges in that tree, just about 1 plus epsilon edges. So next I sample log n trees from this packing. Okay, now for each of these trees, the third step is the following. For each such tree, we find the minimum ST cut that has, let's say, at most 4 edges in any of the sample trees. Okay, and by the property that in expectation I only expect to see 1 plus epsilon edges, that means that if I can find the minimum cut with only 4 edges in this tree, I would be able, that would reveal the actual minimum ST cut. Okay, and so the key property here is that an ST min cut is revealed in this step because the ST min cut satisfies this property that it's sparse in the tree. It has very few edges. Okay, and what the main ingredients in the second part are the isolating cuts lemma, particularly the cut threshold problem, and something called centroid decomposition that allows us to run some recursive algorithms. Okay, and in terms of running time, the first step takes n squared time because the sparsifier contains about O tilde n edges, and we have O tilde n iterations of multiplicative weights update. The second step is just dominated by isolating cuts, so that just takes Polylog Max Flows. And we believe the first step we can actually make that Polylog Max Flows as well, but it's much more complicated than the algorithm I described. Okay, so that's the theorem. On unweighted graphs, we can already show that you can do it in Polylog and Max Flows already in the paper that we have posted. And as I think Saket mentioned a little while back, so a paper was posted yesterday that claims an exact max flow algorithm that runs in almost linear time. So if everything checks out, both our speeding up of Gomori-Hu and this paper that was posted, then we would basically at this point have solved everything that I talked about, all the problems I talked about in almost linear time. So we would have really traversed a long journey. Okay, and with that, I want to end. I'll just put this slide up for students who might be interested in new problems. So basically, I'm saying, can you do anything for directed graphs? None of this works for directed graphs for fairly fundamental reasons. Can you do anything at all? Thank you very much.
Okay. Thanks, Debmalya. So I will clap on the behalf of everyone. Any questions? Okay, I have like a kind of a high level question. So do you feel that the isolating cuts lemma could be useful, like, I mean, I don't know, either to, let's say in the regime of approximation algorithm, so like either to speed up some existing approximation algorithm, or maybe even to break some of the open questions?
So I guess the question is what kind of question,
Yeah.
like what kind of problem. At its heart, what the isolating cuts lemma needs is submodularity and symmetry.
Yeah.
It's really not. It's not really a property of graphs by in an abstract sense. So if you have a symmetric and submodular function, then it's a way of minimizing that function.
Right.
Now, the question is what kind of other situations admit symmetry and submodularity. So some of the other sort of classic examples are things like hypergraphs and so on. But it's possible that there are other situations where you also have symmetry and submodularity, in which case the isolating cuts lemma or an appropriate form of the isolating cuts lemma would still be correct.
But it's mostly to speed up algorithms, I guess, right? Or could it potentially improve approximation factors as well?
That's kind of hard to guess, right? Like, so this distinction is like at a structural level, this distinction between what's useful for speeding up algorithms and what's useful for improving approximation is difficult to make, right? So, for example, all these like new TSP algorithms rely a lot on like cut structure, and in particular cut structure that's polynomial time solvable. So yeah, so that distinction, I'm a little hesitant to make that distinction.
Okay. Any other final questions, thoughts?
So I just had one question there, Debmalya. So like one of the things which like all these classical polytime algorithms has recently used is this expander decomposition, right?
Yeah.
Is there a good literature to read if I really don't care about, say, very efficient computation, but just a good algorithm to understand how it is used or what it is? Like, is there some decent literature for that?
So I guess the sort of most basic paper for just the idea of why there should be expanded decompositions is this thing called cut matching games. I don't know if you have seen that. This is a paper by Khandekar, Rao, and Vazirani. So they don't even talk about expanded decomposition in the paper, but they talk about this thing called cut matching games that are useful for things like sparsest cuts. But it's like that's where the whole idea of expanded decomposition comes from.
I see.
Now, if so you can, like, in hindsight now you can make the connection. It's pretty clear.
Okay.
So that I would say that's the cleanest sort of first paper to read.
Okay. Okay. Thanks.
Sure.
Okay, so if there are no further questions, then let's thank Debmalya for the great talks, like a couple of talks, and thanks once again for staying up past midnight. So
thanks for inviting me and hosting me and coming to my talks. Thanks to all of you. Thank you.